Hi everyone, I'm Fuchen Long from Hygiene.ai. I'm glad to introduce our work, Point Clustering, Unsupervised Point Cloud Pre-training using Transformation Invariance in Clustering. We first go through an overview of our proposal, the new learning paradigm for the unsupervised point cloud pre-training. As we all know, previous unsupervised point cloud pre-training can be grouped into two dimensions, contrastive learning and reconstruction. The former emphasizes the point of seeing discrimination across different views, and the later formulates the pretext task as shape completion. Unlike this existing paradigm, we try to leverage the clustering to learn point features. We iteratively optimize feature clusters and backbone under the feature invariance at two levels, the point level and the instance level. Our proposal is architecture agnostic and readily applicable to different point cloud backbones. Let's go to the details of point clustering. The previous approach of contrastive learning for point clouds is to discriminate the point-wise correspondence between different views. The target is to make the features of the positive pair in different views close to each other and push the negative pairs far away from each other. Inspired from the masked autoencoder in image, recent reconstruction learning paradigm for point clouds pre-training is to learn a point MAE for shape completion. The transformer architecture are usually leveraged for point feature learning. Nevertheless, there is one issue for the above two paradigms. It is that the unsupervised learning is sample-specific. The semantics of instances are not fully explored when conducting point-level discrimination or reconstruction. As such, we leverage the clustering learning to estimate the data distribution holistically and further explore the class-level semantic information. Clustering learning in deep neural networks is not new. Previous work, deep clustering, proposes to iteratively train the deep networks based on the feature clustering results in each training epoch. The class-level data distribution can be estimated, and we proceed along the direction. However, directly apply it for point clouds will ignore inherent geometry of the 3D data, which is not trivial. Therefore, we propose to additionally include two transformation invariants as the inductive bias to regulate clustering learning. Point-level invariance denotes the features of the same point and different data transformation will be similar. Instance-level invariance is the instance feature consistency of objects and different data transformation. Let's first look at the point-level invariance learning. Given a single 3D scene, we first apply data transformation on each scene to generate two views. Then, we apply a traditional density-based clustering approach to the scene to obtain the instance mask. Condition on the mask, we globally pool the point features of each instance to obtain the instance feature. All the instance features are collected as point prototypes in each view respectively. The corresponding clustering assignments are taken as the point labels in each view. Next, for the point feature of each view, we first compute the inner view clustering loss for similarity optimization. Besides, we'll need to make an alignment of the learned clusterings across the two views to achieve the feature invariance during clustering. So we introduce cross-view clustering loss to learn the point features of one view close to the prototype of the same point in another view. Different from the point-level invariance learning on a single 3D scene, the instance-level invariance learning should be conducted on all instances over the entire dataset. As mentioned before, the instance feature is obtained through globally pooling based on the instance mask. Given all the instance features over the entire dataset in two views, we employ k-means to cluster the feature in each view to k clusters. The prototype set and the instance label set are obtained of each view. Similarly, we devise in-view and cross-view clustering loss for feature similarity optimization. The overall training objective of point clustering includes the point-level clustering loss and the instance-level clustering loss. We iteratively measure the network optimization and feature clustering at two levels. We conduct the pre-training on ScanNet dataset, which includes 2.5 million scanning frames, and we extract about 190,000 scans. About 8,000 points of each scan are sampled for training. The downstream task for evaluation includes the object classification, part segmentation, and semantic segmentation. Here is the performances of our point clustering with different backbones on the downstream tasks. Point clustering achieves better performances over the baselines with different point cloud backbone. The evaluation study include different aspects, the invariance learning design and the instance clustering number K, simultaneously leveraging the invariance from both point level and instance level perspectives to explore the geometric properties and semantics will lead to the best performances as shown in the table. From the figure of different performances, pre-trained with different K, given the fact that the backbone is pre-trained on ScanNet, which includes 20 object categories, it is expected that setting the K to around 20 would yield the best performances, but seemingly some amount of over-segmentation is potentially more helpful. Finally, we visualize the point features and show the unsupervised segmentation results. The two results demonstrate the feature discrimination during clustering learning at both of the point level and the instance level. That's all for our works, and thanks for your attention.